Hey everyone, welcome back to Strange New Worlds, a science and Star Trek podcast. I'm your host, Mike Wong. What is science? To me, science all boils down to systematizing change. Look out the window. You'll observe change in the world. We try to document it, create models to understand it, the laws of nature, describe, explain, and predict how things will change from one point in time to another. And we've learned so much by studying change. For one, modern science tells us that the whole universe, at the grandest scale imaginable, is changing. Our universe started out one way, evolved into the brilliant state in which we see it today, and is marching toward something quite different from what we know. But exactly what that end state is, we're not sure, though we have ideas. Today's guest, Dr. Katie Mack, is an expert in those ideas. She's the Hawking Chair in Cosmology and Science Communication at the Perimeter Institute for Theoretical Physics, and the author of the incredible popular science book, The End of Everything, astrophysically speaking. Katie and I are going to talk about the end of the universe, using the Star Trek Deep Space Nine episode Chrysalis as our Star Trek touchstone. In that episode of DS9, a handful of Federation citizens contemplate averting one possible end of the universe, called the Big Crunch, by changing the cosmological constant. And as Katie will explain, that very plot point is a dead giveaway that this episode of Star Trek was written at a very specific time in scientific history. Dr. Katie Mack, welcome to Strange New Worlds, a science and Star Trek podcast.
Thank you. Thank you for having me.
Now, Katie, because this is your first time on the show, I'd like to ask you to share your Star Trek origin story. How did you first encounter Star Trek, and what has it meant to you throughout your life?
I think I must have seen some of the original series when I was very young, but the first Star Trek I was invested in any way was The Next Generation, which came out when I was a child of some form. And I've watched all the other series. I'm not fully up to date on some of the newer ones, but I've always loved Star Trek. I've always loved the kind of outer space adventures, the utopian society kind of stuff. The idea of seeking out new life and new civilizations is just a way of just exploring and trying to understand people. And I like how Star Trek has always been used as a way to comment on life on Earth and society and how things could be better, how things could be worse. I've always really enjoyed that aspect.
Do you think Star Trek played a role in your eventual career as an astrophysicist?
I'm not sure. I mean, I've been interested in all kinds of science fiction my whole life, and so I think science fiction in general has been a big part of why I got into science, in the sense of just being interested in new ideas and exploration and different ways science can do interesting things. I don't think that Star Trek specifically got me involved in astrophysics. The astrophysics itself on Star Trek is not always great, but
true.
But I think it had a bigger effect on me personally than scientifically.
Do you mind sharing a little bit more about that, the personal effect Star Trek has had on you?
I just think that, there are a lot of stories in Star Trek that, kind of make you think about how society is put together, how people treat each other. It's a way of thinking about the future and how things could be. And I think just that sort of general optimism and thoughtfulness about society has had an effect on me as a person. But I don't think it's driven my scientific life per se.
Got it. Yeah, Star Trek has had a profound influence on me as a person as well, and giving me that sort of hopeful, optimistic, that's something that we can try to aim for, or at least inch toward as a society. So, Katie, you're a world-leading cosmologist and science communicator and the author of the best-selling popular science book, The End of Everything, Astrophysically Speaking, which I have here in my hands. It came out back in 2020, but I've got to admit I only just got around to reading it earlier this year, so please accept my sincere apologies for taking so long.
It's fine.
Could you tell us a little bit about why you decided to write this book on the end of everything?
Yeah, so it was a few things. Well, when I was a postdoc, I was doing a lot of popular science presentations, public talks and things like that. And I noticed that one of the things I loved talking about and one of the things that audiences got really engaged in was thinking about kind of the distant future of the universe and how things are all going to go and different kind of scary ideas for the end of the universe. And it's something that just through my career, I've often come back to. I like thinking about the future. I like thinking about, what could happen, and kind of the weird ways that particle physics and cosmology come together sometimes in interesting ideas about both the beginning of the universe and the end of the universe. And so when I was thinking about what to write about, I thought it would be really fun to just kind of go through a bunch of different ways the universe might end. And there are lots of books about the beginning of the universe, and there really aren't that many about the end, or at least, when I was writing it, there weren't any that were recent enough to capture some of the biggest developments in cosmology. And so I thought it would be a fun topic to write about because it's just, they're interesting, fun ideas to work with. I thought that audiences would get a kick out of it because we don't talk a lot about the end of the universe. And I also thought it would be a fun way to tie in a lot of really interesting physics ideas that are relevant to the discussion when you're talking about different ways that the universe could end. So it was kind of all of these things together. And yeah, it turned out to be a really fun book to write. Just really fun to play with all these ideas and to try to work with the kind of this is really scary, but also pretty removed. And so you can kind of find some dark humor in that. And I enjoyed that a lot.
Yeah, it's marvelous that you say that because I found the book extremely informative. I recognized a lot of concepts that I had learned in college and in graduate school taking astrophysics classes, but then I also learned a lot of the more recent cosmology that I haven't kept up with. And at the same time, it was just so funny. I could tell you were having fun writing this book. I was wondering if you could speak a little bit to maybe the use of humor in as a science communication tool.
Yeah, I think that it's helpful when talking about really complex or really heavy topics to use a little bit of humor, partially because I think some people are legitimately scared of the end of the universe. I think that is something that people do freak out about at some level. And there's a sense of kind of horror movie humor you can use there where people, you laugh at this thing that's so scary and so big that you can't comprehend it any other way. But I think also a lot of times people are just nervous about dealing with complex topics, like things where they're not sure they're going to understand the science, right? A lot of people are scared of math. They're scared of something where they're asked to take in an idea and they're not sure if they're going to be able to do it, and it's scary. It's uncomfortable to be in that position where you're I might not be smart enough for this. That's something that a lot of people feel when they're confronted with complex ideas in science. And I think that bringing in humor can help kind of ease that worry a little bit, and build some trust with the audience, being I'm not gonna hurt you with these ideas. I'm not gonna try and make you feel stupid. We're gonna have fun with this. We're gonna go through this together. And that I think can really make it easier to get into some of the deeper, heavier topics.
I love that. I really, really do. I had the great fortune of being able to give a TEDx talk recently, and as you probably know, they give you a lot of training. And one of the things that my storytelling coach taught me was never to try to threaten the sense of identity of your audience. And everybody wants to identify with being smart. And a lot of times when they're encountering new complex ideas, that can threaten their sense of identity as somebody who's capable of knowing things about the universe. And you alleviating that threat through humor is just so brilliant. I love that.
Thanks.
Hey, so speaking about people feeling fear about the end of the universe,
Yes.
Our Star Trek touchstone for today's discussion is the Star Trek Deep Space Nine episode Chrysalis from the 7th season of that show. In this episode, a quartet of genetically engineered humans visits Deep Space Nine seeking medical help for Serena Douglas, who's one of their cohort. And while they're waiting for Dr. Julian Bashir to heal Serena, the rest of them busy themselves with trying to stop the big crunch, which they describe like this.
The fact is that the universe is going to stop expanding and it is going to collapse in on itself. We've got to do something before it's too late.
How much time do we have left?
60 trillion years, 70 at the most.
Oh, no.
Isn't Nog handsome?
What are you doing? We are running out of time. Serena! Thank God. Nobody else around here ever listens to me.
What is it, Jack? What's wrong?
There's too much matter. The universe is too heavy for its own good.
You need to lighten the load.
Yes, exactly. We have to find some way to decrease the mass.
Of the entire universe?
That's the whole point.
Is that possible?
That's what we're trying to figure out, Serena.
What if we found a way to manipulate subspace?
Change the cosmological constant. Yes.
That'd do the trick.
You can't change the cosmological constant.
You know something, Serena? We are trying to save existence as we know it. And all you can do is criticize.
I'm sorry.
Thank you. Now, where were we?
Manipulating subspace.
Right.
Okay, so Katie, let's take this one step at a time. Apparently, the universe is expanding, so let's start there. Why is the universe expanding, and how do we know that it's expanding?
So the second part of that question is somewhat easier to answer than the first part. Why it's expanding, it's expanding because it's been expanding since the beginning. What caused it to start expanding? That's like, the Big Bang is this process where the universe started small and dense and has been expanding since then. And what kicked that off is a different topic, but is still debated exactly how that kicked off. But it has been expanding since the beginning. And the way that we know that is that we see that distant galaxies are all getting farther away from us. And the farther away a galaxy is, the faster it appears to be moving away from us. And that's something that makes sense if you imagine, like you're sitting at the center of a chessboard and there's a bunch of chess pieces around you, and suddenly the chessboard gets twice as big, then everybody's getting farther away from you, no matter where you are on the chessboard. You don't have to be at the center. Everybody will get farther away from you as soon as the chessboard gets bigger. And the people who are already farther away from you, they're getting twice as far away. And so that the speed at which they seem to be receding is much faster than the ones that are closer to you. So, the one square over is now 2 squares over. The one 5 squares over is now 10 squares over. So the 5 squares over guy moved, 5 squares in a second, and the 1 square over person moved 1 square in a second. So there's this relationship where the more distant something is, the faster it seems to be moving if everything is just expanding the same way, right? So the whole universe is getting bigger. We're not in the center of it. There is no center of the universe as far as we can tell. But from our perspective, everything is moving away from us, and the more distant things are moving away more quickly. And so that's how we can tell that the universe is expanding, is because it seems to be that everything is getting farther away from us faster, the farther they are. And we can tell that because there's this cool property of light where as something is moving away from you, the light gets kind of stretched out by the expansion, and so more distant things end up looking redder and redder, and that's called redshifting. That's what we use to determine the expansion speed as everything's moving around. You can think about that in different ways. You can think about it as things moving away from us, or you can think about it as like space is just stretching the light. The latter is probably a better explanation because, nothing's actually moving through space. The space is just getting bigger.
Got it. Okay, and according to one of these characters, whose name is Jack, the universe will eventually stop expanding, reverse course, and collapse on itself because it's too heavy, because essentially it has too much matter. Does that make sense?
Well, so it's interesting. So it was interesting to me watching these scenes because the idea that too much matter means that a big crunch would happen is more or less how people thought about a big crunch when people were first thinking about the concept of a big crunch as this idea that maybe the expansion will stop and reverse. When it was thought that it was going to happen, the thinking was that basically, the Big Bang started out this expansion, but matter, like the density, the gravity of everything in the universe is kind of slowing the expansion down, right? And so it should be slowing the expansion down because all the matter is pulling on everything else. Like imagine in that chessboard, if everybody's kind of like pulling toward each other with ropes or something, and they're anchored to the ground, they can slow that expansion of that chessboard, right? And we knew that this expansion had been slowing, like it was faster in the beginning, and it's been slowing as time goes on, just because there's a whole bunch of stuff gravitating, and it should be pulling things together. And so when in like the 60s, it was thought that the big crunch was the most likely explanation for the future of the universe because it was thought that we had so much matter that it was going to slow the universe so much that the universe would stop expanding at some point and collapse again. And so in the sort of 1990s, astronomers tried to figure out how quickly is the universe slowing down in its expansion. Is it slowing down so much that it will stop, or is it slowing down in a way where like it'll slow down, but it'll always keep expanding, just, it'll keep expanding forever, but it'll slow down. Those were kind of the two possibilities people were thinking about. And so they were trying to measure this deceleration parameter, this number that would tell them how quickly the universe was slowing down. And when it was actually measured in the 90s, it was a negative number. What that means is that the universe is not slowing down at all. It's actually speeding up in its expansion. And so when that was discovered, it really changed how people thought about the end of the universe and, what the universe is made of. And we came up with this concept of the cosmological constant, which is a sort of aspect of space-time that kind of makes it stretchy and makes it sort of expand, on its own in a way that would cancel out and overcome the pulling together of all the matter. So now we don't see the big crunch as the most likely thing because the universe is not slowing down in its expansion. It is speeding up. And so, it was interesting in this episode because there was a point later where somebody mentioned the cosmological constant. It's like, well, if you know about that, then you should know. So it was an interesting idea. But the topic of, the idea that like too much matter would mean collapse, that is fair. Like if you have too much matter density, too much gravity, that can slow and stop expansion. It's just that currently the data is not pointing that way. Now, the data are getting a little bit complicated right now in ways we can talk about in a bit because there are some interesting new results around that. But I think that like what we call the concordance cosmology or the sort of usual default idea about cosmology is that the cosmological constant is governing the expansion now in the sense of like the expansion is speeding up, it's going to keep speeding up, and it's never going to recollapse. That's what is sort of the default assumption right now based on the bulk of the data.
Got it. Wow. Okay, so that's really interesting that, back when this episode was being written, maybe the leading theories were the universe was going to slow down in its expansion, but keep expanding ever so slowly, or it would actually turn around and collapse because the universe was too heavy. But now we know better that the universe is actually accelerating in its expansion.
Well,
yeah.
When was this episode aired, actually? I'm curious about that.
1998.
Okay, so 98 was exactly the year that this acceleration was discovered and attributed to a cosmological constant. So
wow.
I don't know which side of that this episode came on. I mean, I think there were suspicions that the expansion wasn't slowing that much, but it wasn't until 98 when the data were really clear that expansion was not slowing at all. So people, let me think, the idea of the cosmological constant had been around, but not taken as seriously as it was after that result. So yeah, it'd be interesting to ask the writers, like, which part of this did you know about?
Yeah. And it seems like the episode is a reflection of that kind of transition point because it mentions both the Big Crunch idea and the cosmological constant. So they were both floating around and, accessible to the Star Trek writers at the time. And they sort of just bashed them together. Fascinating. So Jack does give a time scale for the Big Crunch. He says it'll happen in 60 to 70 trillion years. If the Big Crunch were to happen, does that seem like a reasonable time scale?
I mean, that seems short to me, but I don't know. I haven't looked at these Big Crunch models specifically in a while, so I'm not sure. I'm not sure what the estimates were at the time when the Big Crunch was in vogue. But I think that. Yeah, I mean, maybe that's a reasonable estimate. The estimate that I mentioned in my book when I was thinking this through was like it had to be, the universe is at worst middle-aged, right? Like, and the universe is currently 13.8 billion years old. So, we're talking about trillions of years. I guess that could be a plausible time scale, depending on what model you have, how overdense the universe is. You get different time scales for when the collapse could, when the expansion would stop and then when it would turn around. So I'd have to do some calculations. I don't want to put anything anything concrete out there, but it doesn't strike me as wildly implausible, although I would estimate probably a bigger number based on the data at the time, but I'm not sure.
Got it. Okay. And finally, this trio of folks comes up with two proposed solutions. Number one, decrease the mass of the whole universe, or two, change this cosmological constant. So, Katie, I want to have you imagine that you're a peer reviewer and these two proposals come across your desk. How would you rate them? Is either of them possible?
I mean, so as far as we know, neither is possible. However, I definitely would lean toward the changing the cosmological constant, because if you just dial up the cosmological constant a bit, then you can prevent collapse. That's kind of how these things are, work together in the equations. The cosmological constant is something that, if it's positive, promotes expansion and can, balance out the matter. So you can dial up the cosmological constant, get more expansion, stop a big crunch. Now, to be fair, the universe does end eventually. Like, with a cosmological constant, you just get a different end of the universe, and it takes a different amount of time, potentially. Like, you get what we call the heat death, or a big freeze, where the universe gets so spread out, so diffuse, that basically things stop happening and everything decays away. But if you want to specifically stop the big crunch, making the universe less massive is a tricky concept, because it's like, okay, how do you do that? Are you removing mass from galaxies? Is that screwing up all the galaxies? This could be really bad. But just changing the cosmological constant, you're not going to affect galaxies themselves necessarily. You could affect, the sort of growth of structure in terms of like how galaxy clusters come together and things like that. But it's going to be fine. You're just going to change how quickly empty space is stretching. So that's great. So, if you can change the cosmological constant, and I know that they do say in the episode you can't change the cosmological constant, and that's a sort of plot point about like, this character getting sort of chided by her friends for saying that, but so probably you really can't. However, if you're going to go one way or another, that's the way I would do it. I was a little disappointed that the end of the episode did not clarify what they chose or what they were going to do if they came up with an answer to this. But,
Yeah. Well, as we spoke about, the episode was written in 1998, when the idea that the universe could end in a big crunch was much more widely held. But a lot has happened in cosmology since then. Right around that time, we were making discoveries that changed our view of the universe's end, including the discovery of this cosmological constant, which I believe you can equate to dark energy, right? They're sort of synonymous. Is that right?
Well, so dark energy is the term for the phenomenon, whatever the phenomenon is that's making the universe accelerate in its expansion. A cosmological constant is one possibility for that. There could also be kinds of dark energy that are not constant. So the thing about a cosmological constant is it's something that's just built into space-time. It's just built into the structure of space-time. It doesn't change over time. It's just a part of how space and time and the universe work. And so that you can kind of predict how it's gonna affect the expansion over time and so on. There could be kinds of dark energy where the dark energy changes over time in some way. Maybe it becomes more powerful, less powerful, and it would act like a cosmological constant, but it wouldn't be constant. So those are kind of the distinctions. Dark energy is the term for whatever's making the universe expand faster. It might be a cosmological constant. It might be something known as dynamical dark energy, or sometimes called quintessence, a kind of dark energy that doesn't stay constant.
Got it. Thanks for making that distinction clear between the cosmological constant and dark energy. Now, what exactly were the discoveries that we made that changed the way that we viewed the end of the universe? Why do we no longer think that the Big Crunch is likely?
Well, yeah. So in 1998, there were a couple of studies that came out that showed that the expansion of the universe was accelerating, and in order to get accelerated expansion, you need some kind of dark energy. And it also, kind of puts away this idea that the universe is going to slow down and stop, right? If it's accelerating, it's hard to imagine that it accelerates for a while and then slows down and then stops. Like there's many extra steps. And especially if it's a cosmological constant, then it can't slow down and stop once it's accelerating. That's the acceleration is because the cosmological constant has now become the most important sort of feature of the universe, and it's going to stay that way as everything else kind of diffuses away in the expansion. Now, that said, what that did is that set up what we call the concordance model of cosmology, or sometimes called lambda CDM, where lambda is the character we use to denote the cosmological constant in our equations, and CDM stands for cold dark matter, which is the dominant form of matter in the universe. And I guess we're probably not getting into dark matter today, but it's a kind of invisible matter that is most of the matter in the universe. So lambda CDM is the sort of model of the universe where it's dominated by a cosmological constant and this cold dark matter. And both of those things are mysterious, so it's an interesting model that's based on two things we don't understand. That's the concordance model. And that's been the dominant model for decades. There are some interesting results as of recently that point toward maybe a possibility of dynamical dark energy instead of a cosmological constant, instead of lambda. Specifically, there are some galaxy surveys, mostly this one called DESI, the Dark Energy Spectroscopic Instrument. This is an instrument that's been used to study dark energy by looking at distant galaxies and measuring things about how they're distributed through the universe, essentially. And that study has an interesting hint of a possibility of dark energy becoming less powerful over time, which, if that's the case, then that would point toward dynamical dark energy. So it would point away from a cosmological constant, but also point toward something where if dark energy becomes less powerful, then that slows the acceleration. And you could imagine a scenario where it slows enough that the acceleration stops, the expansion could stop, and the universe could turn around. There's not currently like a model that's been put out there of like, here's what that'll look like. It's just there's these kind of hints where maybe dark energy is changing. And so for some people, that's put the idea of a big crunch back on the table. I don't know if I would go that far. I would say that it's still very preliminary. The evidence is kind of mixed. I don't know that we can really say too much about it right now, but it is interesting that, for the first time, there's really intriguing data kind of pointing towards something other than the cosmological constant or other than the concordance model. And it's just a matter of, getting more data and doing more analysis to see if that evidence sticks around, or like so much else in physics, if it just turns out to be, a statistical glitch. Sometimes you just get a blip where an unlikely result shows up because you've done a whole lot of observations, and you just get unlucky in what you measure. Sometimes there's a systematic error, we call it, where there's some part of it that wasn't calibrated quite right, and when you get better data, you redo the whole process, and you find that the answer is something different. So we don't know if those things will happen. We don't know if the evidence will get stronger over time or go away. But it's an interesting time for cosmologists for sure, because now a lot of people are thinking about different possibilities for dark energy, which is cool because as scientific phenomena go, the cosmological constant is not so easy to study. It doesn't do anything particularly interesting. It just is built into the universe and makes it expand faster. It's basically just a number. And so having something that's like changing over time that might be related to like a fundamental field in the universe, that would be really fun and interesting. So cosmologists are intrigued by these ideas.
Fascinating. So it's changing times yet again in terms of what we think is on the table in terms of possibilities for the end of the universe, which makes me want to ask, if the Star Trek writers called you up tomorrow and said, hey, Dr. Mack, we need your help writing an episode about the universe's end, what would you tell them the end of the universe should look like?
I mean, I think that still the most likely end is a heat death, this kind of big freeze, the kind of like everything just kind of decays away and dissipates into nothingness. I think that's still what is, best supported by the data at this point. Unfortunately, it's a very dramatically uninteresting end of the universe. A lot of times I tell people about the heat death and they're like, it can't possibly be that anticlimactic. It can't possibly be that sad and boring where everything just fades away and freezes and we're all left alone in the dark. Like that seems too sad, too boring, too depressing. And so a lot of people like ideas like cyclical universes where the universe would end and begin again in some way, or something more dramatic. A lot of people think that a heat death is it's too undignified an ending, but I do think that the data are kind of pointing more in that direction than others.
Now, in the book, I learned about another kind of end to the universe that is sort of the opposite of the Big Crunch in a way. It's called the Big Rip. Could you describe that one? I mean, that would alleviate people's concerns about a boring end, right? That's the opposite of boring.
Yeah. So a Big Rip it's a version of the end of the universe where dark energy is dynamical, but gets more powerful over time. And in a very specific and probably physically unfeasible way, it gets more powerful to the extent where it's not just moving things apart in the universe. I mean, the way that the cosmological constant works, galaxies get farther away from each other, but the galaxies themselves are not really affected. But a Big Rip scenario would be a kind of dark energy we call phantom dark energy, where it would be able to actually pull apart bound structures. So it would pull apart galaxies and stellar systems and planets and all of that. And so if you go through the calculations with a phantom dark energy scenario, you get a point where the whole universe is just ripped apart. Everything in it is torn asunder, and the whole universe just kind of gets torn apart. And so that's definitely a more dramatic end. It's, I think, a scary one because you would see it coming. You would see, things starting to drift away in the universe in a way that you'd be able to kind of calculate what's coming. But yeah, that would be very dramatic, and there would be, a time scale that you could calculate for that. And based on what we know now, or at least the last time I calculated the time scale based on like current data, the earliest possible end in that direction would be something like a couple 100 billion years. I think now the data are better, and maybe you get something else. Although with dynamical dark energy, all bets are off. We don't know. And interestingly, some of the interpretations of this dynamical dark energy possibility from the DESI survey results suggest that maybe dark energy could have been of the phantom variety in the distant past of the universe, which would suggest that it's not physically impossible, but then that's very dependent on how you analyze the data. So I wouldn't go so far as to say that like it definitely was that. But it's an interesting thing that people are talking a little bit more about phantom dark energy now than they were when I wrote the book because of this new result.
Fascinating. Okay, so just to summarize for my own comprehension, it seems like the fate of the universe really hinges on what the actual nature of dark energy is. If it's dynamical and it weakens over time, there's a chance that there could be a big crunch. If it's just a cosmological constant or doesn't weaken enough, we're headed toward a heat death. And if it's dynamical and actually goes up with time, then we might be in store for a big rip.
Yeah, more or less, yeah. Yeah, we need to know what dark energy is.
So imagine you're in this conversation with the Star Trek producers and they're like, okay, we've established that, one of these possibilities is going to be the end of the universe. What would be the technobabble infused way that our Star Trek heroes could possibly avert such an end?
That's tough because I think none of these are things that there's any conceivable way you could affect them. I think that if they're talking about tapping into subspace and changing the cosmological constant or something, if there were a way to affect the energy field that is dynamical dark energy, if that's the scenario they're going with, then it would be a matter of like tweaking that. I don't know how you do that through the whole universe, so that's another question. But it would be something to do with altering the scalar field, it's called, that is the dark energy in that scenario.
So moving forward in the next couple of years and decades, it sounds like one of the biggest open questions in cosmology is what exactly is the nature of dark energy? How are we going to try to answer that?
There are a bunch of things you can do to study dark energy. I mean, it's difficult because we're talking about something that is spread through all of space evenly, as far as we can tell, and does not interact with anything other than like space-time itself. So it doesn't interact with light or matter in any way that we can tell. It just stretches space. So basically the tools you have are you can look at the expansion history, so you can see how space has been expanding over time and try and match that with models that you have for what dark energy should do. You could also look at the history of like the growth of structure. So by that I mean how matter comes together to make galaxies and clusters, and that's going to be affected by what the space-time is doing around it, like how space is stretching. So you can look at those kinds of things. The DESI survey is looking at kind of the statistical distribution of galaxies as a way of measuring something about how the expansion has been happening over time. There's not a whole lot else. If you have some kind of dynamical dark energy, some kind of field, some of them have interactions with other components of the universe. So some of them have interactions with matter, with certain kinds of other energy fields in different ways. And so there are some scenarios that give you the possibility of laboratory experiments that could tell you something about it. And so people are, of course, constantly pursuing those possibilities as well. There hasn't been anything definitive found there, but people look for signs in laboratory experiments of interactions with some kind of field or new sort of forces in the universe that might be connected to that. They call fifth force experiments. So we have electricity, magnetism, the weak force, the strong force, gravity. So fifth force would be some new force in the universe. So people look at those kind of possibilities as ways to study certain models of dark energy. But generally, you've got expansion and you've got growth of structure, and there's not a whole lot of other sort of observational handles on dark energy.
Got it. Okay, so exciting times ahead in terms of trying to figure out what dark energy really is, and sounds like you have a lot of work ahead of you.
Yeah, there are a lot of like surveys, like galaxy surveys and things that are coming up that are going to tell us a lot. New telescopes that are going to get better surveys of galaxies in the universe, way more galaxies, supernovae, all these kinds of markers of structure in the universe. So we're definitely getting way more data, and even things like gravitational waves can tell us some things about dark energy by being connected to how the expansion works over time. Because gravitational waves are just waves in space-time, and so things that are affecting the expansion of space-time can affect those too. So there's definitely a lot of data. I don't want to make it sound like we're at a loss. We have tons of new data coming, new observational projects, but it's not something where you can do experiments on it in a lab. Usually, for most of the models, you're constrained to looking for a couple of different kinds of features in the data, and then it's just a matter of being more sophisticated and more creative about how to do that.
Got it. Well, I look forward to following this work and maybe reading about it in a second book of yours. So, to begin to wrap things up, I actually read your book earlier this year because I've got a student working with me on some science policy stuff. She's a law student, but is interested in switching into astronomy. And so together we've been reading a bunch of books to figure out which area of space science she's most interested in. And of course, I said, well, if you want to learn about cosmology, we've got to read Katie Mack's book. So we're reading these books together, and then she'd ask me questions about them. And there was one question that really stumped me that I couldn't answer.
Okay.
And I'm going to just pass it on to you. So my student asked,
Sure. Which
of the leading cosmological theories for the universe's end do you feel is least depressing?
Yeah, so I definitely find the Big Crunch scenario the most scary, the most horrifying, because it's you get sort of crushed to death by radiation and matter, and it just sounds awful. And it would also be one you would see coming. So that one and the Big Rip are both quite scary from that perspective, and not happy endings. The heat death, you get the longest amount of time to deal with things. So that seems good. People call it depressing because everything kind of peters out, but I feel like, you've got a lot of time, so that's nice. A lot of people find the bouncing scenarios less depressing than others because you could have a new universe that comes out of the end of ours, which, I think that one of the things that people find reassuring about it is the idea that something of us will live on. That's not necessarily an option for some of these scenarios. So it's, we'd just be replaced. But whether that's good, as a sort of consolation prize, I think a lot of people find some hope in that. There's another scenario we didn't talk about here called vacuum decay, which is a scenario in which there's a kind of quantum event somewhere in space that kind of resets some of the sort of settings for how physics works in our universe. And that would destroy the universe very quickly in a way that you would not see coming. You wouldn't even notice it. And it could happen at any time. Probably won't happen for, trillions and trillions and trillions and trillions and trillions of years. But I like that one, as I find that one not depressing because you wouldn't even notice it. It would be so quick and so painless. It just kind of resets the universe entirely. So I feel like, I don't know if that one or the heat death are the least depressing for me, but definitely, the others are, if not depressing, just terrifying.
All right. Great answer. Katie, I'd love to give you this time to plug any upcoming projects of yours that you think our audience should know about.
Well, yeah. So you mentioned a book. I am working on a second book. It's not about cosmology, though. Yeah. So this one's not about cosmology. This one's more about particle physics and about how kind of the subatomic world connects to what we understand about how the universe works, both on the small scales and the large scales. So I am deep in edits on that project now. It's called How to Build a Universe.
Wow.
And it should be coming out sometime roughly a year from now, I think, we're looking at early 2027. So that's in progress. And other than that, I'm working on a couple of things with the Perimeter Institute. I'm working on a podcast for that. We've only recorded a couple of episodes so far and nothing's come out yet. So I don't want to put too much out there yet, but hopefully we'll be doing a new kind of podcast. Perimeter already has a cool podcast that's about what people at Perimeter do. It's interviews with people here, but this is going to be a slightly different one. It's, I don't want to say too much about it, but it's got a bit more of a sci-fi connection, so I think that'll be a lot of fun. So, you can keep track of that through like I put some things on my website sometimes, astrokatie.com. But I also have a currently sort of defunct newsletter that I've been meaning to revive. And there's a place to sign up for that on my website. It's called Watch This Spacetime. And I'm also on Blue Sky, astrokatie.com on Blue Sky. And on Instagram, I'm Astro Katie Mack, although I don't post a whole lot of science on Instagram. I mostly post about flying airplanes and stuff because it's much more picturesque. But, being a video and visual medium.
Fantastic. Wow. Can't wait for your new book. Good luck with that and your podcast as well. Can't wait to learn more. So thanks. Katie Mack, thanks so much for joining us on Strange New Worlds and walking us through the end of the universe.
Thanks very much for having me. This was fun.
If you haven't done so already, make sure you check out Katie Mack's book, The End of Everything, astrophysically speaking. It's one of the most informative and entertaining popular science books I've ever read, and it comes with my highest recommendation. Next time on Strange New Worlds, we'll be joined by two of my colleagues, philosopher Patrick Anderson and astrobiologist Kayla Smith. Together, Kayla, Patrick, and I just published a new paper that we think you'll want to hear about. Until then, stay safe, stay curious, and I'll see you out there.
Sorry, I'm drinking tea and I've done it wrong.
No worries.